Reasoning about time. Stream processors often need to deal with time, especially when used for analytics purposes, which frequently use time windows such as the average over the last 5 minutes. It might seem that the meaning of the last 5 minutes should be unambiguous and clear, but unfortunately the notion is surprisingly tricky. In a batch process, the processing tasks rapidly crunch through a large collection of historical events. If some kind of breakdown by time needs to happen, the batch process needs to look at the timestamp embedded in each event. There is no point in looking at the system clock of the machine running the batch process, because the time at which the process is run has nothing to do with the time at which the events actually occurred. A batch process may read a year's worth of historical events within a few minutes. In most cases, the timeline of interest is the year of history, not the few minutes of processing. Moreover, using the timestamps in the events allows the processing to be Roman too. Thank you to Costas Cloudas from the Flink community for coming up with this analogy. Deterministic. Running the same process again on the same input yields the same result. See fault tolerance on page 422. On the other hand, many stream processing frameworks use the local system clock on the processing machine, the processing time, to determine windowing. This approach has the advantage of being simple, and it is reasonable if the delay between event creation and event processing is negligibly short. However, it breaks down if there is any significant processing lag, i.e. if the processing may happen noticeably later than the time at which the event actually occurred. There are many reasons why processing may be delayed. Queuing, network faults. See unreliable networks on page 277, a performance issue leading to contention in the message broker or processor, a restart of the stream consumer, or reprocessing of past events. See replaying old messages on page 451 while recovering from a fault or after fixing a bug in the code. Moreover, message delays can also lead to unpredictable ordering of messages. For example, say a user first makes one web request which is handled by web server A, and then a second request which is handled by server B. A and B emit events describing the requests they handled, but B's event reaches the message broker before A's event does. Now stream processors will first see the B event and then the A event, even though they actually occurred in the opposite order. If it helps to have an analogy, consider the Star Wars movies. Episode Roman 4 was released in 1977, Episode V in 1980, and Episode VI in 1983, followed by Episodes I, Roman 2, and Roman 3 in 1999, 2002, and 2005, respectively, and Episode Roman 7 in 2015. Roman 2 if you watched the movies in the order they came out. The order in which you process the movies is inconsistent with the order of their narrative. The episode number is like the event timestamp, and the date when you watched the movie is the processing time. As humans, we are able to cope with such discontinuities, but stream processing algorithms need to be specifically written to accommodate such timing and ordering issues. Confusing event time and processing time leads to bad data. For example, say you have a stream processor that measures the rate of requests counting the number of requests per second. If you redeploy the stream processor, it may be shut down for a minute and process the backlog of events when it comes back up. If you measure the rate based on the processing time, it will look as if there was a sudden anomalous spike of requests while processing the backlog, when in fact the real rate of requests was steady. Figure 11-7. Figure 11-7. Windowing by processing time introduces artifacts due to variations in processing rate. Knowing when you're ready. A tricky problem when defining windows in terms of event time is that you can never be sure when you have received all of the events for a particular window, or whether there are some events still to come. For example, say you're grouping events into 1-minute windows so that you can count the number of requests per minute. You have counted some number of events with timestamps that fall in the 37th minute of the hour, and time has moved on. Now most of the incoming events fall within the 38th and 39th minutes of the hour. When do you declare that you have finished the window for the 37th minute, and output its counter value? You can time out and declare a window ready after you have not seen any new events for a while, but it could still happen that some events were buffered on another machine somewhere, delayed due to a network interruption. You need to be able to handle such straggler events that arrive after the window has already been declared complete. Broadly, you have two options. Ignore the straggler events, as they are probably a small percentage of events in normal circumstances. You can track the number of dropped events as a metric, and alert if you start dropping a significant amount of data. Publish a correction, an updated value for the window with stragglers included. You may also need to retrack the previous output. In some cases it is possible to use a special message to indicate, from now on there will be no more messages with a timestamp earlier than T, which can be used by consumers to trigger windows. However, if several producers on different machines are generating events, each with their own minimum timestamp thresholds, the consumers need to keep track of each producer individually. Adding and removing producers is trickier in this case. Assigning timestamps to events is even more difficult when events can be buffered at several points in the system. For example, consider a mobile app that reports events for usage metrics to a server. The app may be used while the device is offline, in which case it will buffer events locally on the device and send them to a server when an internet connection is next available, which may be hours or even days later. To any consumers of this stream, the events will appear as extremely delayed stragglers. In this context, the timestamp on the events should really be the time at which the user interaction occurred, according to the mobile device's local clock. However, the clock on a user-controlled device often cannot be trusted, as it may be accidentally or deliberately set to the wrong time. See clock synchronization and accuracy on page 289. The time at which the event was received by the server according to the server's clock is more likely to be accurate, since the server is under your control, but less meaningful in terms of describing the user interaction. To adjust for incorrect device clocks, one approach is to log 3 timestamps: the time at which the event occurred, according to the device clock; the time at which the event was sent to the server, according to the device clock; the time at which the event was received by the server, according to the server clock. By subtracting the second timestamp from the third, you can estimate the offset between the device clock and the server clock, assuming the network delay is negligible compared to the required timestamp accuracy. You can then apply that offset to the event timestamp, and thus estimate the true time at which the event actually occurred, assuming the device clock offset did not change between the time the event occurred and the time it was sent to the server. This problem is not unique to stream processing. Batch processing suffers from exactly the same issues of reasoning about time. It is just more noticeable in a streaming context, where we are more aware of the passage of time. Once you know how the timestamp of an event should be determined, the next step is to decide how windows over time periods should be defined. The window can then be used for aggregations, for example to count events, or to calculate the average of values within the window. Several types of windows are in common use. Tumbling window. A tumbling window has a fixed length, and every event belongs to exactly one window. For example, if you have a 1-minute tumbling window, all the events with timestamps between 10:0300 and 10:0359 are grouped into one window, events between 10:0400 and 10:0459 into the next window, and so on. You could implement a 1-minute tumbling window by taking each event timestamp and rounding it down to the nearest minute to determine the window that it belongs to. Hopping window. A hopping window also has a fixed length, but allows windows to overlap in order to provide some smoothing. For example, a 5-minute window with a hop size of 1 minute would contain the events between 10:0300 and 10:0759. Then the next window would cover events between 10:0400 and 10:0859, and so on. You can implement this hopping window by first calculating 1-minute tumbling windows, and then aggregating over several adjacent windows. Sliding window. A sliding window contains all the events that occur within some interval of each other. For example, a 5-minute sliding window would cover events at 10:0339 and 10:0812, because they are less than 5 minutes apart. Note that tumbling and hopping 5-minute windows would not have put these two events in the same window, as they use fixed boundaries. A sliding window can be implemented by keeping a buffer of events sorted by time and removing old events when they expire from the window. Session window. Unlike the other window types, a session window has no fixed duration. Instead, it is defined by grouping together all events for the same user that occur closely together in time, and the window ends when the user has been inactive for some time. For example, if there have been no events for 30 minutes. Sessionization is a common requirement for website analytics. See group by on page 406. Stream joins. In Chapter 10 we discussed how batch jobs can join datasets by key, and how such joins form an important part of data pipelines. Since stream processing generalizes data pipelines to incremental processing of unbounded datasets, there is exactly the same need for joins on streams. However, the fact that new events can appear anytime on a stream makes joins on streams more challenging than in batch jobs. To understand the situation better, let's distinguish 3 different types of joins: stream joins, streamed table joins, and table joins. In the following sections we'll illustrate each by example. Say you have a search feature on your website, and you want to detect recent trends in searched for URLs. Every time someone types a search query, you log an event containing the query and the results returned. Every time someone clicks one of the search results, you log another event recording the click. In order to calculate the click-through rate for each URL in the search results, you need to bring together the events for the search action and the click action, which are connected by having the same session ID. Similar analyses are needed in advertising systems. The click may never come if the user abandons their search, and even if it comes, the time between the search and the click may be highly variable. In many cases it might be a few seconds, but it could be as long as days or weeks if a user runs a search, forgets about that browser tab, and then returns to the tab and clicks a result sometime later. Due to variable network delays, the click event may even arrive before the search event. You can choose a suitable window for the join. For example, you may choose to join a click with a search if they occur at most 1 hour apart. Note that embedding the details of the search in the click event is not equivalent to joining the events. Doing so would only tell you about the cases where the user clicked a search result, not about the searches where the user did not click any of the results. In order to measure search quality, you need accurate click-through rates, for which you need both the search events and the click events. To implement this type of join, a stream processor needs to maintain state. For example, all the events that occurred in the last hour, indexed by session ID. Whenever a search event or click event occurs, it is added to the appropriate index, and the stream processor also checks the other index to see if another event for the same session ID has already arrived. If there is a matching event, you emit an event saying which search result was clicked. If the search event expires without you seeing a matching click event, you emit an event saying which search results were not clicked. In example, analysis of user activity events on page 404 figure 10-2 we saw an example of a batch job joining two datasets, a set of user activity events and a database of user profiles. It is natural to think of the user activity events as a stream, and to perform the same join on a continuous basis in a stream processor. The input is a stream of activity events containing a user ID, and the output is a stream of activity events in which the user ID has been augmented with profile information about the user. This process is sometimes known as enriching the activity events with information from the database. To perform this join, the stream process needs to look at one activity event at a time, look up the event's user ID in the database, and add the profile information to the activity event. The database lookup could be implemented by querying a remote database. However, as discussed in example, analysis of user activity events on page 404, such remote queries are likely to be slow and risk overloading the database. Another approach is to load a copy of the database into the stream processor so that it can be queried locally without a network round trip. This technique is very similar to the hash joins we discussed in map-side joins on page 408. The local copy of the database might be an in-memory hash table if it is small enough, or an index on the local disk. The difference to batch jobs is that a batch job uses a point-in-time snapshot of the database as input, whereas a stream processor is long-running, and the contents of the database are likely to change over time, so the stream processor's local copy of the database needs to be kept up to date. This issue can be solved by change data capture. The stream processor can subscribe to a changelog of the user profile database as well as the stream of activity events. When a profile is created or modified, the stream processor updates its local copy. Thus, we obtain a join between two streams, the activity events and the profile updates. A stream table join is actually very similar to a stream-stream join. The biggest difference is that for the table changelog stream, the join uses a window that reaches back to the beginning of time, a conceptually infinite window, with newer versions of records overwriting older ones. For the stream input, the join might not maintain a window at all. Consider the Twitter timeline example that we discussed in describing load on page 11. We said that when a user wants to view their home timeline, it is too expensive to iterate over all the people the user is following, find their recent tweets, and merge them. Instead, we want a timeline cache, a kind of per-user inbox to which tweets are written as they are sent, so that reading the timeline is a single lookup. Materializing and maintaining this cache requires the following event processing. When user U sends a new tweet, it is added to the timeline of every user who is following you. If you regard a stream as the derivative of a table, as in figure 11-6, and regard a join as a product of two tables UV, something interesting happens. The stream of changes to the materialized join follows the product rule UV equals of plus UV. In words, any change of tweets is joined with the current followers, and any change of followers is joined with the current tweets. When a user deletes a tweet, it is removed from all users' timelines. When user U1 starts following user U2, Recent tweets by U2 are added to U1's timeline. When user U1 unfollows user U2, tweets by U2 are removed from U1's timeline. To implement this cache maintenance in a stream processor, you need streams of events for tweet sending and deleting and for follow relationships following and unfollowing. The stream process needs to maintain a database containing the set of followers for each user, so that it knows which timelines need to be updated when a new tweet arrives. Another way of looking at this stream process is that it maintains a materialized view for a query that joins two tables, tweets and follows, something like the following. The join of the streams corresponds directly to the join of the tables in that query. The timelines are effectively a cache of the result of this query, updated every time the underlying tables change. Roman 3.